There are two examples of fluxional behavior that we are going to talk about today, and the first being something called a Berry pseudo-rotation. So let's see what this is, and then maybe we can come back and define what is this fluxional behavior that we're describing. So let's imagine that we had PF5. And so this is a structure we talked about previously when we talked about isomers. And so we have this picture that we can draw where we have both equatorial and axial positions for our fluorines. And so we describe that these are in fact different positions, right? So we can call these the axial positions. And then we have our three equatorial positions. And if we were going to study this, spectroscopically, what we would see is if we ran an IR, right? If we ran an IR, we would see two different PF stretches. Right, so we want to remember that IR spectroscopy measures the energy for these bond stretching frequencies, right? And so this makes sense because we have a PF equatorial stretch and PF axial stretch. We talked about how those are different bond lengths, which means that they would have different force constants for their vibration. Um, and so it makes sense that we would see two different PF stretches. However, if we take the same structure and we were going to run an NMR, right, and let's say we ran a fluorine NMR, we would only see one fluorine signal, right? And I'm putting some exclamation marks here because this is pretty surprising, right? We have these equatorial positions and these axial positions. And through IR spectroscopy, we can see that there's two different stretches. And yet with the NMR, we are only seeing one fluorine signal. And so that must mean that on the time scale of an NMR, right? So on the time scale of an NMR, the equatorial and axial positions can switch places. Or exchange. Now, the reason this works out is because IR is a very fast spectroscopy. And what I mean by fast spectroscopy is I mean that IR is measuring bond vibrations. Bond vibrations occur very quickly. And so if we have something that exists for longer than a few bond stretches, we can actually see it in IR spectroscopy. However, NMR spectroscopy tends to be much slower, right? So it has a much longer time scale for NMR spectroscopy. So we must be seeing something that's occurring here, right, where we have an exchange between these axial and equatorial positions. And so if we're going to try to draw out what's happening here, right, let's look at a slightly different compound just so we can see it easier. So we also showed this in our previous video. Right, so PFCl4. And here we have that fluorine that is in our axial position. This follows Bent's rule, right? That we put our more electronegative atom in the axial position for these 5 coordinate complexes. And so what we're saying is that on some time scale, right, given some amount of energy, we can actually see this exchange occur where we end up with our fluorine in an equatorial position and we end up with our chlorines in these axial positions. And for right now, all we can say is that this particular exchange is faster than NMR. And so what we're seeing when we take this NMR is actually an averaging of these two different signals because they're going back and forth so quickly, right? So that one signal that we see is really the average of the axial and equatorial signal. Now, if we were going to cool this down, and we cooled it significantly down, where we made it to where we could no longer see this exchange occur, we would actually see two separate signals come out. And so this is a temperature variation or a temperature effect, meaning that this is only talking about at room temperature, the rate of this exchange. We could cool this down and we could see two separate signals occur. If we also got this as a solid, right? So if we were able to crystallize this compound somehow, we would no longer have these rapid exchanges, and we may be able to actually see a difference between the axial and the equatorial fluorine positions. So this process is called a Berry pseudo-rotation. And so we can see this over here in kind of our learning goals. This is Berry pseudo-rotation. That's what's happening here for this 5-coordinate complex. Now in class, what we're going to do is we're going to do a little bit more practice here of seeing these Berry pseudo-rotations. And what we're going to do in class, using a short activity, is we are going to identify the transition state. Right? And now this transition state won't quite be the same as the transition states we saw in organic chemistry because we aren't making or breaking any bonds. This transition state is just the middle point in this conversion, right? The point between our two different trigonal bipyramidal complexes. And so I'm kind of leading in saying that like this is a point between the trigonal bipyramidal complexes. And so this transition state we're going to look at is actually of a different geometry. All right, and so we're going to do a little bit of an investigation on that in class when we dig into this. However, this isn't our only example of fluxional behavior. So like I said, we wanted to see an example of fluxional behavior, and then we were going to try to describe it. So this idea of fluxional just means changing, right? And so these structures can change, they can rotate, they can move, and we can observe these changes using spectroscopy. So we can see the difference in the NMR and the IR that explains the difference between the axial and equatorial positions. So let's apply this to a haptic ligand set, right? So here we have our learning goal or objective number 3 is apply this fluxional behavior to haptic ligands. So we've described these haptic ligands before, where we have a metal center that's actually bound to multiple atoms in a row. So let's look at this given rhodium complex that has two different phenyl rings attached. That's not a very good one. Let me redraw it. As a chemist, I have to be able to draw polygons, right? So if I have an ugly polygon, I got to erase it and try again. And on this complex, we're going to look at one that is overall +1 charged, right? So it's this cation. And so this is something else that came from our first quiz that needs a little bit of practice, is not losing track of these charges. They influence the oxidation state and our total electron count. So let's look at our total electron count for this rhodium complex. So we find rhodium on the periodic table, right? And that's the first step that we do. And we see that rhodium brings with it 9 electrons. All right, we know these phenyl rings are 6 electron donors, right? They are L3 type donors. And there's 2 of them, right? So that means that we have 2 times 6 electrons just from those phenyl rings. And then lastly, we need to account for our charge. And so this is a cation, meaning we lose 1 electron from our count, right, for this being a cation. And so what we're left with is a 20 electron complex. And this doesn't look too bad, right? We've seen 20 electron complexes before. There was an example of a nickel aqua complex that was 20 electrons. But now, right, we don't necessarily have to be 20 electrons. So using this idea of hapticity and the idea of our different bonding modes of benzene, how might we get down to 18 electrons? Well, one way to do that is actually to change the hapticity of our ligands, right? So as this is drawn, these are both our eta-6 benzene configurations. But if we were going to imagine, right, that we weren't necessarily stuck with eta-6, what if we had an eta-4 benzene that was bound to our rhodium, and this is still the cation, right? So now we still have an eta-6 benzene, and we have an eta-4 benzene. Now this eta-4 benzene looks like an L2 type ligand, which is a 4-electron donor. So if we're going to count up our electrons, we have our rhodium, which is 9 electrons. We have our eta-6 phenyl, right, which is 6 electrons. We have our eta-4 phenyl, which is 4 electrons. And we still have our cation, right? It's positively charged, so we're going to lose that 1 electron here. So now if we add this up, we see that we get to an 18-electron complex. And we can even see, right, that this benzene is distorted on the bottom. Right? It's kind of bent out from being planar due to this different sharing of electrons. And in fact, if you get a crystal structure of this, you can see that the benzene structure is slightly deformed, right? Meaning that there is some truth, right, to this picture that we can draw. However, if we were going to catch an NMR of this at room temperature, we would only see, right, we would only see one proton signal, right? One proton NMR signal at room temperature. Right, and that's because this is constantly changing, right? We can go between the eta-4 and the eta-6 configuration. This process has a different name than a Berry pseudo-rotation. This is called ring slipping, right? And this is just a way for us to account for different electron counts. It's a way for us to get to 18 electrons. And also it explains some kind of interesting things that we see in spectroscopy. If we were going to cool this down, we could actually start to see this bottom benzene ring distort. And we can see not only that distortion in a crystal structure, but we could also see it in NMR spectroscopy. And so we have two different types of fluxional behavior, right? This behavior that causes our molecules to exchange their ligands, to have their ligands move around and behave differently. The first being that Berry pseudo-rotation of 5-member or 5-coordinate compounds. And now we have this idea of ring slipping for haptic ligands. And both of these are ways that we can adjust to different electron counts, right? Whether it is higher or lower than 18 electrons. We can have some kind of ring slipping that moves around some electrons and changes our bonding. But it also has some impacts on spectroscopy. So we're going to do a little bit more practice with this in class, but we just want to be thinking about how these molecules are not just static, right? We draw this picture on the slide and we think, well, they just stay this way. That's not true, right? These molecules are constantly rotating and twisting and bending and stretching. And we want to remember that when we're thinking about these physical structures that we can draw, because molecules don't care how we draw them, right? This is going to be really helpful as we get into symmetry, which we're going to be talking about later on this week and through next week, because we're going to start thinking about how do these different groups relate to each other, right? So today we talked about isomerism, right? The different types of isomers of inorganic compounds and how we can describe them. And now we've talked about this fluxional behavior, meaning how our ligands can change places and change their reactivity and explain observable phenomena, right? In this case, we might be able to see different peaks in an NMR. We might see a distorted crystal structure. And how can we use our understanding of bonding to explain these differences? All right, so I will see you in class.